Hello, everyone. Welcome to the 6th Annual Women in Microscopy Conference. If this is your first time joining us, welcome. And if you've attended before, welcome back. And happy early International Women's Day, which is March 8th on Sunday. My name is Tirza Abbott. I am the manager of the SEM facility here at the NUANCE Center at Northwestern University. I am also a PhD candidate in the Earth and Planetary Sciences. And if this is your first time here, to give you a little bit of a backstory, about 6 years ago now, which is incredibly hard to believe, during the height of COVID, my very good friend and colleague Stephanie Ribbit and I were working in the labs here at Northwestern. Stephanie, at the time, was a graduate student here. She is now a staff scientist at Lawrence Berkeley National Labs Molecular Foundry in the National Center for Electron Microscopy, or NSEM. But at the time, like many of you, we were missing conferences and the opportunity to learn from each other about our research and just connecting with friends and colleagues. We were also very interested in finding a way to highlight the work and achievements of women in microscopy. So we started this event as a way to bring people together, to celebrate the incredible work being done by women in our field, and to create a space to learn from one another. Since we started this conference, it has grown into something very special. We've welcomed trailblazing women in microscopy as keynote speakers from national labs and academic institutions. We've hosted panel discussions on important topics such as diversity and inclusion, navigating careers in science, and outreach. And over the years, we've welcomed hundreds of participants from across the country and from around the world, with attendees joining us from 20 or 30 different countries each year. We've also done our very best to make it a priority to highlight early career researchers, giving them a platform to share their work, and to feature women working across a wide range of microscopy-related careers who can share their experiences and perspectives with our community. Now, things have shifted a little bit. In 6 years, we are now back in person for conferences and events. We've made a few changes to the format this year. The program is a little bit shorter and more streamlined, so we don't spend too much time at our computers on Zoom, but the heart of the conference still remains the same. We are all here to celebrate the amazing work being done by women in microscopy and to learn from each other. From the beginning, this event has been a collaboration between the NUANCE Center and the Microscopy of America Student Council, and now the Early Career Council. For those of you who may not be familiar, I am here at the NUANCE Center, which is an open access user facility at Northwestern University that provides cutting-edge analytical instrumentation and expertise to researchers from academia, industry, and national labs. This year, the NUANCE Center is also celebrating its 25th year in operation, which we're very proud of. If you'd like to learn more about us and what we do, we will be sharing information at the break today. And with that, I am very, very pleased to welcome you all here today. And I'm going to turn things over to representatives from the MSA Student Council and Early Career Council, who will introduce themselves and say a few words.
Hello, everyone. I'm Ece Günay. I'm a fourth-year PhD student at Carnegie Mellon, and I currently serve as the Secretary of the Microscopy Society of America Student Council. It's my great honor to welcome you all on behalf of the Student Council to this year's conference. There will be more information about the Student Council during the break. And if you have any questions or if you know students who might be interested in joining us, I may encourage them to join us. Please feel free to shoot me an email and I'd be happy to connect and chat afterwards. With that, I'd like to thank the organizing committee and I hope you enjoy the program.
Hi, I'm Joy Chow, and I am a staff scientist at Oak Ridge National Lab. I am the co-chair for the Early Career Committee, which was formed just last year, actually. Our goal is to advance the careers of early career individuals and help bridge that gap after a terminal degree and offer opportunities for job and funding things through professional development, educational outreach, and networking events. So yeah, I am really glad that we were able to support this microscopy conference and hope you all enjoy.
So I will go ahead and introduce our keynote speaker. It's a great honor to be introducing Barrett Googe. She received her BA in physics from Carleton College, and then her PhD in applied physics from Cornell University. She was a presidential postdoctoral fellow at UC Berkeley before moving to Germany as a SMICH Science Fellow and Minerva Group Leader at the Max Planck Institute for Chemical Physics of Solids. She's returning to Cornell in July 2026 as the Faculty of Applied and Engineering Physics to establish a lab that seeks to push the limits of advanced electron microscopy for understanding and designing functional quantum materials. So with that, Barrett, please go ahead, share your screen. We're really looking forward to your presentation.
Great, thank you. Okay, let's see. We just rehearsed, so I'm going to see if we can.
Got it.
Sorry. Okay, good. Good. Hopefully you can see my screen.
Yes, that looks perfect.
Okay, there used to be a pointer. We'll see if it comes back, but otherwise I'll talk you through it. So yeah, thank you so much to Steph for the introduction and Tirza and everybody for organizing. I think this is like such a cool event, and I was like completely amazed and honored to even get the email for the invitation, especially when you look back through sort of the prior speakers. So I'm just going to do my best and hopefully just like what I want to share today is, what I'm really excited about, which is leveraging these amazing tools that we now have access to be able to sort of chart uncharted territory at the scale of atoms in novel quantum materials and other kinds of materials. So as Steph said, the only thing I'll really say about my journey is my foray into electron microscopy really started during my PhD at Cornell. I had no intention or really no idea about electron microscopy or what it was. But by a very happy trick of luck, I ended up in an amazing research group and just loved the research and loved what I was doing there. And so I was very fortunate to have, a great time in my PhD and then to be able to move to Germany to try something really new. And so I'll kind of try to give you a sense of a little bit of how my step away from microscopy in Germany, I think kind of interfaces with this field of science that I really love. And so super excited to be moving back this summer. I'm actually at Cornell. I'm on campus just this week, so it's really fun timing and to be sort of launching a new group here and hopefully give you a sense of some of the projects that we hope to tackle as we get underway. Okay, so I remember like learning in middle school, right, that the atoms are the building blocks of the universe, and I think this I took it for granted or I accepted it. That was all fine. And it really wasn't until I came to Cornell for my PhD that I actually got to see this with my own eyes, right? And I got to use an advanced electron microscope and really see all of these, okay, the cursor is gone, but hopefully you see what I'm pointing at. All of these bright dots that tell us that these materials really are made of atoms, and those atoms really are stacked together in the case of crystalline materials in these amazing ordered patterns, right? And it's sort of all of the world around us. It's everything is made of something. This is the slogan of one of the departments here on campus. And so whether it's, from enamel from a human tooth, like you see here on the left, whether it's from a geologic specimen, this is from a 600 million year old rock that was picked up from Antarctica. So very different conditions in those two materials. Or, which is more the focus of my research, whether it's a synthetic compound that was grown and stabilized very carefully and very painstakingly many times in a laboratory, because teeth and rock are useful and have their own sort of properties. And what we're trying to do as material scientists and as quantum materials researchers is really trying to kind of bring a new level of control to these compounds so that we can design whatever kinds of functions we might be interested in for sort of future technologies. And so the sort of phrase that we're using now in the field these days is called quantum materials. And this is what we call them. They've, the same materials have gone through other kinds of names in the past. And so I'll tell you why in a minute, but usually when we say, we study quantum materials, these are kind of like forward-looking, potentially technologically relevant materials. And some of them are a little bit closer to application or a little bit more likely to end up, let's say, in your computer chip or a quantum computer or some kind of energy device. And some of them are a little bit more fundamental. But usually the kinds of properties that we're interested in them because they could give us a new way of kind of devising functional devices, right? And so the transistor, for instance, is based on semiconductors. And this has completely revolutionized how we all live our lives, right? With computers and digital technology and what. And so we're kind of looking at what is going to be the next sort of semiconductor revolution. What is the next silicon and what sort of devices are those going to enable for technology. But why are they called quantum materials? It's not just because they might someday end up in a quantum computer. It's actually because as sort of materials physicists, what we need to kind of move beyond a classical or a nearly classical understanding of how these materials come together, right? And so the nearly classical picture is sort of, maybe you think of an electron as like a particle moving, through a through a lattice or something. But to really understand the properties of quantum materials, we have to invoke other sorts of degrees of freedom and other kinds of order parameters. And so we need to step away from this kind of classical picture, and that's where the word quantum comes in. So the idea is we need to sort of know something, the properties of the materials, people will say, are governed by quantum mechanics, right? And so what this means from a more practical level, so some people are out there deriving Hamiltonians, that's not me, so often, but from sort of our standpoint, what this means is that the kinds of ingredients which define what quantum materials do are some of these four things, like what you see on the screen. So of course, it's the atomic lattice. Which atoms are they? So which elements are you using? They all have their own different properties. And how are those arranged in different kind of configurations? And that, of course, can change the properties of materials. The classical example there would be, for instance, graphite versus diamond, right? Both of those are carbon, but they have very different structures and very, very different properties. But moving beyond just the atomic lattice, we're also interested, for instance, in the configuration of the electrical charge in these materials. How do electrons move? How do holes move? How are they arranged? Are they ordered? Are they disordered? Those kinds of things. Similar conversation for orbitals, which helps us understand how the electrons are interacting between atoms of maybe different kinds or different lattice sites, different types of hybridization, as well as not just what the electrons are doing in a sort of charge sense, but actually what kind of spins might those electrons be carrying, or might the atoms be carrying. And so this is when you start talking about spin, that's really where you get into magnetic materials. And so you can think of these sort of up and down arrows as almost like little north and south poles on a magnet, right? And so you can imagine that if you have a whole bunch of spin up electrons, a whole bunch of up-oriented spins in your material, this is what we would call a ferromagnet, so like the thing that you stick on your fridge. But there's other kinds of magnets, and so maybe you have these sort of up-down alterations, that would be an antiferromagnet, and there's all kinds of other sort of rich magnetic textures that can be useful for different properties beyond just hanging artwork on the fridge. And so it's very kind of convenient, or very lucky, or makes us so excited to study these quantum materials with the electron microscope, is that you might already be recognizing in advanced, especially transmission electron microscopes, these are some of the things that we can actually measure very well. So of course we can measure the lattice. I've already shown you some pictures of beautiful atomic structures, but with spectroscopies, we can measure things like charge and orbitals if we look at electron energy loss spectroscopy. And with some other kinds of imaging, for instance, Lorentz TEM and other things like that, we can also access the spin texture and the magnetic texture. And so what this means is that advanced electron microscopes really give us very deep insight and very high resolution insight into some of the most fundamental kind of properties or fundamental ingredients, again, that drive the properties in these materials. Okay, so the title of the talk was Atomic Architecture, and this is kind of an analogy that I like to give to kind of help people understand what do I mean by electron microscopy for materials design. And so I'm not there today, but for the past several years, I've been living in Dresden in Germany. So this is former East Germany. It's a beautiful historic city with a much longer history than that, going all the way back. It used to be the seat of the Saxon Empire. So if you're ever in Germany, it's not central, but it's worth a trip. And there's this very famous cathedral right downtown called the Frauenkirche. So this is the Cathedral of Our Lady. So it's a beautiful historic building. Okay. Now, I actually grew up in northern Minnesota, and we're coming out of the winter, but I think many people in the Midwest, maybe the folks in Evanston also can feel this, I think had kind of an intense winter this year. And, there are weeks when it gets very cold and you've got to sort of occupy your time in the winter. And so one thing that, you see sometimes in Minnesota and in many other very cold places, for instance, are these kind of ice house constructions or igloos, if you will. Right. And so here you see two very different buildings. They obviously serve very different purposes. They each have their pros and cons, depending on what it is you're looking for in a building. And you can appreciate the engineering and the skill that goes into constructing both of them. Right. And if you take a closer look at each of these buildings, they do have some commonalities. They're not completely unrelated to each other. So in this case, they're both constructed of pretty similar looking kind of fundamental bricks. And those bricks are actually sort of laid together in very similar ways, right? We have these rectangular blocks that are stacked together in a pretty well-ordered fashion. And so probably you can see where this is going, right? The analogy there, I think, is pretty nice to these kinds of crystalline materials, where again, what we can do is if we make the bricks out of sort of different ingredients, instead of ice bricks or stone bricks, we can use different elements and we can stack them together, and variations of the same motif will have different properties that we can try to tune and we can try to optimize based on the use case that we might have in mind for this material. So that's kind of the overarching approach to what I call atomic architecture. And where the microscopy comes in, I think, really strongly is, for instance, that if we take a much closer look down to the building blocks, we can even learn something much richer about the material, right? And so in this case, the sort of differently colored bricks that you see here on the Frauenkirche have to do with its reconstruction after it was destroyed in World War II. So there's a lot of, very deep history that we can learn by looking not just at the sort of complete object of the cathedral, but really zooming in all the way to that most fundamental level. And so that is kind of the approach that we take to quantum materials. We want to consider them as a whole. What do they do? What can they bring to the table? How do we design that? And how can we learn about those details by looking all the way down to the atomic scale? And so this, I think, is a kind of image that will be familiar to many people. But this is a good representation of a lot of the types of data that I work with. So this is a high angle annular dark field, or a HADF STEM image. And what you see on the top is this strontium copper oxide material, which has been actually grown in a very careful method that I'll tell you a little bit more about, on top of this other terbium scandate material. And so again, you can see from the microscopy perspective, we can clearly tell the two materials apart. We can observe a very abrupt interface. And the question is, how can we look closer into that lattice to learn something rich about both of these materials? Okay, so that's kind of a big ask. There's a whole lot of materials out there in the world. Even if you narrow it down to quantum materials, you're still left with really quite a lot. And of course, it takes a long time to set up these experiments. And so we can't look necessarily at everything all the time. We have to focus down a little bit more. And so what I want to kind of tell you about today, I'm going to pick one particular class of quantum materials and give you a few examples of how the electron microscope has been really, I think, really important in understanding their development. Okay, and so one phenomenon that I've been working on, actually by accident for several years, is superconductivity. And so many people may have heard of superconductivity. Some people may be more familiar, some people less familiar. But the sort of key distinction of superconductivity that many people think about, you see over here on the left. This is a drop to absolutely zero resistance, zero electrical resistance in the material, which means that if you try to push current through it, there's no electrical losses. You don't lose any current to heating or anything like that. So it's 100% efficient conduction of electricity. And they also, related to that, expel magnetic fields. And so that's this thing that you see over here on the right. The sort of levitating chunk is a piece of superconductor. And it's actually levitating above a magnet because it's actively expelling those magnetic fields. And that force is enough to keep it elevated in the air. And so maybe from just those two properties, you can already in your mind start to think about why we might, as a society, be very interested in superconductors. So again, I mentioned, 100% efficient energy transmission. There's this, statistic that people sometimes throw out, which is, well, if you, covered like half of Nevada in solar panels, you could generate enough electricity for like the full United States or something like that. Don't quote me. But the challenge is not only that you have to convince half of Nevada to put solar panels, to cover their land with solar panels, but actually getting that energy from Nevada, for instance, all the way up to the Northeast, like in Ithaca or in Maine, you lose a huge amount of energy through that transmission because most of our electrical transmission lines are not super efficient. And so in a kind of dream world, you could imagine, well, if I can move electricity from where it's generated to where I want to use it without any losses, then you don't have to always have such a strict balance of like people not wanting to live next to where the electricity is generated. They're also potentially useful for things like quantum computers. That's a big one for superconductors. And the magnetic levitation that you see over on the right is very important for things like, for instance, if you want to do a levitating magnetic train, so those for high-speed travel, but also for generating very high magnetic fields. And so if any of you have ever had an MRI, like a medical MRI, that huge gigantic coil or tube that you go into is actually full of superconducting coils. So they're very useful. We would love to have more superconductors. We do have a lot of superconductors, but the problem with many of them is that the superconductivity is a very low temperature phenomenon. And so really a lot of times in superconductivity research, we're interested in understanding how superconductivity arises in these materials, but especially with the goal and the idea that if we understand it well enough, we could actually design a superconductor at much higher temperatures. And so there's this kind of holy grail that people talk about, which is the idea of room temperature superconductivity. And so most of these properties that I told you about are like down, near 10 Kelvin, not super practical for lots of technologies and in everyday life. So superconductivity research has been going on now for over a century. You see from this is a sort of overview of a bunch of different superconductors, the year in which they were sort of first discovered or announced, and then the y-axis is that critical temperature. So that's the temperature at which the material actually becomes superconducting, and you need to be below it if you want to take advantage of that property. And so you can see that the first discovery was mercury, so all the way down on the bottom left in 1900. And it has a very low critical temperature, right? Just a few Kelvin. And then you can see that over time, we have discovered more and more superconductors. Those temperatures are coming up. Again, I don't have the pointer, but okay, you see in the middle, there's all these blue diamonds. These are the superconducting cuprates, also known as the high TC cuprates, because you can see their temperatures are much higher. And we'll come back to those in a minute. This is the discovery of those in 1986 was really a revolution in the field of condensed matter physics. But you can see there's all kinds of other families, right? These orange squares are iron-based superconductors. And there's other materials which superconduct, for instance, these green circles that you see up in the top right. The temperatures are very high, so 250 Kelvin's not very cold, but you see that that only happens at 170 gigapascals of hydrostatic pressure, which is like an insane amount of pressure. So again, if you wanted to put that in your cell phone, it's not going to work so well. So I actually had to extend the x-axis on this plot a little bit from the one that gets shown around quite a lot. And so the superconductors that I've been working on, especially and that I want to tell you about today, are these two families in the sort of star shapes that you see over here on the right side of the plot. So in the kind of bright magenta, we have what I will call square planar nickelates, and I'll describe to you what all of this means. And then in the kind of top teal stars, you see we also have another family of nickel-based superconductors. And so these two families are kind of, people will say we've entered the nickelate age of superconductivity. And so there's been a lot of work you can see in just the past sort of 5 to 6 years of the discovery of these materials, trying to understand them and trying to learn as much as we can so that we can hopefully keep pushing those temperatures up and up and up. Okay, so again, so how does this process of, I want to walk through the process maybe of materials discovery and materials design and use these superconductors as an example. And so you can sort of think about, if I go back to this plot and you can think about superconductors, right? It's this big general thing. And you could ask, well, what's the best superconductor? And that's a little bit like asking, well, what's the best dessert, right? So there's a lot of really great desserts in the world, but they're very different from each other. And it's maybe not easy to compare, let's say, your favorite ice cream to your favorite pie, right? Because it might depend on the day and it might depend on what you're looking for. And so the same is true for superconductors. If you want to design the best superconductor, you need to contend with all kinds of different things. And so what temperature do you want to use it at, but also how robust does the superconductivity need to be? For instance, how easy does it need to be to manufacture? Like, are you planning to make power cables or are you planning to make little tiny micro devices? And so all of these questions kind of have different ways that we can approach these different superconducting families. Okay, but if you want to go out and you want to set out to make a new superconductor, you can kind of extend this dessert analogy a little bit more, right? And you could say, well, gosh, I really love, this apple pie that I eat every Thanksgiving, and it's my favorite dessert, but my garden doesn't have any apples in it. It only has plums. And so obviously the thing that you could do is you could take inspiration from the apple pie that you know and love, and you could say, well, what if I, instead of using apples, decided to use plums? And so that's one way that we can approach materials design, is to work off of sort of a known entity. And so this is where those copper oxide superconductors that I told you about are going to come back into the story. And so it's actually a very exciting year in condensed matter physics, because you see the publication date on this reference that I show you here on the right. And so this is the first discovery of superconductivity in copper oxide superconductors, actually in any oxide superconductor. It was very surprising because up until then it had been sort of metals and alloys only. And so these ceramics were very surprising. But you can see from the date that this was now 40 years ago, and it was actually 40 years ago this month in March. And so, there's a big physics meeting coming up in a couple of weeks, and it's a big sort of to-do for 40 years of high TC cuprates, right? So this was really revolutionary. And since this discovery, there's been a whole bunch of different families of cuprates. You saw many of the sort of labels on the previous slide. But you can ask yourself, well, what do they all have in common? And over the years, people have kind of distilled it down to a few sort of key ingredients. And so one, of course, as the name cuprate implies, is the presence of copper, and actually of copper and oxygen. And in particular, in this kind of atomic configuration where you see here, the purple balls are those copper ions, and then they're in this kind of square net of oxygen. So they form these kind of square layered planes. And also all of the cuprates have this sort of D9, what we call a D9 electron configuration, right? And so if you think about copper and you do your electron counting and you balance all with the stoichiometries of the crystal, what you find is that you have copper 2 plus in this material, which means you have 9 D electrons, and they're sort of arranged in your 5D levels like this, right? So 9 out of 10, which means you have 1 sort of electron and 1 hole up in the uppermost energy level of those D bands. Okay, so people, were very excited about this, this sort of revolution of the cuprates, and they were mixing all kinds of different compounds together and trying to always push up TC, and it went up, and it's now like 150 Kelvin, so that's very exciting. But they already were starting to look and say, how can we go beyond, right? And so one obvious thing that you can do is you can consult your periodic table. And you can look at copper, and then if you just go one over, you see nickel. And so you could say, well, what if I put nickel in there instead of copper? Would the thing still work? And so actually going back now more than 2 decades, so not so long after the discovery of cuprates, this idea was already occurring to people, right? And so there's some theoretical discussion about a possible analog of using nickel instead of copper if you could put it in that same atomic and the same sort of electronic configuration we have in the cuprates. So that prediction was made in 1999, and it finally turned out to be true. So here's the atomic structure you see here. We've just tipped those planes down, and those are now nickel oxide planes instead of copper oxide planes. And you see the kind of comparison of the resistivity over here on the left. So very exciting. Nickel-8 superconductivity finally demonstrated, but not until 2019. Again, so there's 2 decades between the prediction and the stabilization of these materials. And just to assure you, this is not for lack of trying, and it's not for lack of dedication or lack of talent on the people who were trying, right? This is it turns out to be an incredibly hard synthesis problem. So the reason it's hard is because you want to get that same D9 configuration in the nickel, which means if you go backwards and you count your electron valence, you need to have a monovalent nickel or a nickel 1 plus, right, to keep everything neutral. And so if there are any people who study nickel-8s in the audience or nickel-based compounds, you might know that nickel 1 plus is actually not a stable valence. And so what that means is that this compound you see pictured here on the right is sort of thermodynamically metastable, and you can't synthesize it directly. Nobody's ever been able to figure out how to do that. So one of the kind of key breakthroughs that came in several years ago to allow this kind of possibility is the idea that you grow first a more stable nickel compound in this D7 configuration. So you can see a comparison of the atomic structures. And then you perform a chemical reaction to actually extract some of those oxygens. So if you look at the chemical formulas on the top, you go from a rare earth nickel O3, you take out 1/3 of those oxygens, and you end up at rare earth nickel O2. So again, I don't want to get too bogged down in the details, but just to kind of emphasize that this is, it's a long and winding road through kind of materials prediction, synthesis, and discovery. And so to really, emphasize that it takes a lot of very talented people working for a very long time to try to get all of these pieces in place. And so we're very lucky as electron microscopists to eventually get to participate. That's my opinion. So you can see here, for instance, with the annular bright field STEM images that I'm showing you, we can image directly that removal of oxygen as you go from the image on the left, where you see all of those oxygens surrounding every purple nickel ion, to the image on the right, where you can see the oxygens above and below that ion are missing from the structure. So this is great to kind of help the synthesis confirm that it's the correct phase that we're interested in. Okay, so now we're going to talk about this phase over here on the right. This is the sort of nominally superconducting phase. And so by the time you go through this very complicated synthesis, you've got to grow a film, which is kind of hard to grow anyways, a material which is hard to grow anyways, and then you've got to do this kind of really aggressive chemistry to it. And it's not so surprising that, the first sort of batches that came out, although they showed superconductivity, when we do a STEM image and we go in and we look at these materials, you can see that it's not exactly what we would consider a perfect lattice, right? And so there's a lot going on, but you can see from the STEM image that in this sort of green box, there are regions which look basically like we think they should look. So they look very high quality. But in all these other colored boxes, there are regions which are something else, right? So the two red boxes kind of above and below highlight just the substrate. So the sort of platform that the material is actually grown on. All of these superconducting nickelates are grown as very thin films. You can see it's only about 10 nanometers thick. So you have to grow them on top of something else. In this case, it's the strontium titanate material. But you also see, for instance, in the blue and the yellow and the purple box, these regions that are kind of secondary or defective crystalline phases, right? And so it's kind of messy. There's a lot going on. And that's fine. The thing still superconducts. There's still a lot we can learn from these samples. We're not sitting here waiting for the most perfect crystal to emerge. But it's important to know, and it's important to keep in mind as we go and we want to actually learn about the physics of these materials so that we can, again, kind of keep going on this journey to understanding and designing better superconductors. And so in particular, if you want to do something, if you want to learn about the electronic structure, you want to do some kind of spectroscopy, for instance, you need to know about all of these different phases that exist in the material, because you can see from these kind of isolated sections that I have here by eels, they're each contributing their own spectroscopic signature, right? And so there's all these different spectra that are coming out. And you can imagine that if you're just doing a bulk spectroscopy, from X-rays or whatever, and you can sample only everything on average, that's going to give you not exactly just the signal from the region that you're interested in. So one of the key advantages that we have with a very local measurement like STEM is that we can actually go in, we can find the regions which are the thing that we're interested in studying, and we can just do very local measurements to target, in this case, the spectra or the spectroscopy of just those kind of locally pristine regions. So it's kind of a double-edged sword. On the one hand, we can see everything that's wrong with the material, so we can help to kind of optimize the synthesis. We can help the folks who grow these materials understand what may have gone wrong and where there's room for improvement. But at the same time, and in parallel, we can kind of do some shortcuts and we can work around those imperfections that persist, and we can still kind of advance ahead of schedule while they're still doing the optimization to try to figure out some of these more fundamental questions. Okay, so this is what we did in the case of these sort of first discovered superconductors. I'm not going to go too much into the details. I'm happy to talk with anybody who's maybe more interested. But what you see here are oxygen K-edge eel spectra from those kind of local clean regions. So again, kind of pulling out just the crystalline regions that we're interested in. Of 4 different compounds, you see this sort of blue through red gradient. And what we're doing here is we're slightly changing the electronic dopings or the carrier concentration in these materials. So what we do is we substitute some of the neodymium, in this case for strontium, which slightly changes the average nickel valence. And so you kind of, instead of a D9 in the blue case, you might have like a D8.8 in the sort of purple case, right? And so this is actually how you tune superconductivity in these materials. So what we wanted to know is what's really going on electronically as we go across these kind of superconducting, through these different superconducting phases. And what you see is this very sort of subtle shoulder that starts to emerge under where I've marked with the black arrow. And so this was actually the sort of feature that we went out looking for. And it was very hard to find because we were working based off of this kind of old cuprate literature, where you see a very similar emergent feature, again, with this whole doping. But you can see that with the arrow and the cuprates, it's much stronger signature than it is in the nickelates. And so ultimately what this tells us from a physics perspective is that these two materials are not exact analogs. It turns out there are some important differences between the nickelate superconductors and the cuprate superconductors as we understand them now. We're definitely still working to understand them. We don't know everything. But for me as like a PhD student taking on this project, I think it was also like a really great lesson in sort of, well, in many things, first of all, but in grit. And so in kind of continuing to do these measurements, we kept measuring and measuring, and we were about to give up. And I told my PhD advisor, I want to just do this last measurement just so I can say, honestly, we've tried everything we could possibly think of. And only then did we finally see the signature, right? So I think it's good to kind of keep pushing through the tough parts. But also it's in the details of this paper, which again, I'm happy to talk about, we had to really carefully optimize this experiment. And so, we needed exactly the right microscopes and exactly the right experimental conditions. And that I think speaks to me, something else that I love about, the microscopy community that I know, which is like how collaborative and how willing everybody is to help. And so especially at Cornell, we're really lucky to have like a really amazing facilities staff. And so being able to work with all of those tool managers who could really help make sure that everything is running really at the kind of top level so that we can get the data that we need. Okay, so we're learning about the electronic structure of these nickelates. Again, these experiments, I think, could only be done through electron microscopy, and they've helped us kind of point to some key differences between these nickelates and their cuprate analogs, which is really important information for the theorists to kind of feed back into this cycle of materials engineering. But I mentioned that at the same time, we're also trying to optimize the synthesis so that we can actually start to kind of get rid of some of these secondary phases, because although we can work around them, for other people and other measurements, they can be problematic. And so we want to also, in sort of parallel, be pushing towards materials, better optimized materials. And so one of the things that can make it hard to optimize these materials is something called epitaxial strain. So I mentioned that this is a thin film of a nickelate compound, which is deposited on top of something else, so some kind of support platform. And so if you have these two materials, like what I'm showing here in this cartoon, they all have their, lattice constants, right? So it's a crystalline material, and there are characteristic distances spacing out all of the atoms. And so if these two materials have sort of similar symmetry, similar shapes, they're both in this case, let's say cubic, and they have very similar lattice constants marked by this ruler A, then you can put one on top of the other without any problem, right? You can just put it down, and there's some other technicalities, right? But in principle, it works very well, and everything is nice and happy. Now, the challenge is that if you want to take that top material, in this case, the yellow one, and you want to, for some reason, put it on top of a material with either a much smaller or a much larger lattice constant, like you see on the left and the right, then you can imagine that as you put the yellow material down, something has to happen. It has to accommodate its structure because it still wants to maintain all of these atomic bonds. And so what can happen if you're very careful is that you can actually stabilize different kinds of what we call strain. And so you can see that the material distorts itself to fit onto that bottom layer. And so on the left, you have what we would call compressive strain. So as you put something onto a material with a smaller lattice constant, it gets kind of squished in, but then it expands outwards to kind of make up for it. Versus on the left and then on the right, what you see is tensile strain. We put that material down and it stretches out, but then you see it kind of compresses in the other direction. So we're going to come back to strain a few more times. So I just want to kind of get everybody on the same page. This is sort of the picture you can have in your mind. We're using the substrate to push and pull on the lattices of these materials. Now, that can be very useful, but it can also be very challenging because you can imagine that kind of a crystal doesn't want to be pulled on, right? It has a lattice constant that it wants for a reason. That's where it's stable energetically. That's where it wants to be. And so you can pull on it for a while. That's what you see here. So there's a substrate down at the bottom and there's a nickelate film on top of it. And overall, the crystal structure looks pretty good. But as you grow these materials thicker and thicker and thicker, what you can see is that eventually the strain is just too much and the material kind of relaxes and stabilizes all of these sort of other secondary phases, right? And so you can see all these kind of columnar features coming in. Those are formed as the nickelate tries to sort of alleviate that. In this case, there's a tension that it was feeling from the STO substrate. So there's this very careful kind of threading the needle of Goldilocks zone to try to get a strain which is in some cases useful for the material, but not so much that you can't stabilize high quality materials. So again, that's kind of an extreme example, but there's more subtle cases. And so we can see this very clearly in the electron microscope. So here I'm mapping out these sort of defect phases, which form as a function of strain. And so you can see comparing two different films from about 3 years apart, that the one on the top is quite a bit messier than the one on the bottom. And that's because these are grown on two different materials. And so it turns out that this bottom material, LSAT, has a better lattice match with the nickelate film. And so you're able to stabilize a higher quality structure. And it doesn't just look nicer in the electron micrographs, it also improves, again, the properties of the materials, which is ultimately what we're really interested in, right? Is having a nice material that does something interesting or useful. And so you can see in this case, for instance, that actually that superconducting transition, that vertical line from the red to the blue trace has actually gone up by several Kelvin. And so that's a really big improvement for the kind of superconducting properties in these materials, which we can see is really directly related to understanding the lattice properties and the lattice structure as well. So over the past now about 5 to 6 years, we've been in this kind of ongoing cycle of optimizing the synthesis of these materials, readdressing scientific questions. Everything I've shown you so far is these neodymium nickelate materials, so strontium substituted neodymium nickelate. But it turns out that just like the cuprates, there's all kind of chemistries which work out. You can use different rare earths. You can use lanthanum or praseodymium or samarium. You can use strontium, calcium, europium. And actually, you don't even need to dope the films as well. You can do kind of structural variations. And so with very advanced layer by layer synthesis by molecular beam epitaxy, you can even, instead of doping these materials through a chemical substitution, you can actually just dope them through structural control of the lattice. And so what you see here are sort of 5-layered versions of those materials. It's basically 5 layers of what I've shown you, separated by a spacer and then another 5 layers. And you can tune that 5 to other numbers. So here you also see kind of an 8-layer version or a 6-layer version. And we're working on understanding how these materials kind of relate. They seem electronically similar to the ones I've just talked to you about, but they have different sort of they might have different signatures of dimensionality. So as you confine the sort of properties into those thinner and thinner layers, you can sometimes get other interesting effects that emerge. And so that's one of the things that we've been working on lately. So again, throughout all of this work, we've taken lots of images, we've seen lots of films, but part of this has been all part of a broader effort in the field of nickelate superconductivity to try to understand what we call the phase diagram of these materials, right? And so for us, the phase diagram on the x-axis is this hole doping. That's that electronic tuning that I told you about, and the temperature. And so you can see that we have this kind of green region of superconductivity. And so for some kind of chemical range, down at temperatures around 20 Kelvin is where we get superconductivity. So that's all been a lot of exciting development, a lot of effort in this field. And sometimes I get asked by people, well, why don't you just go look at the superconducting phase? Can't you just look at the material? And so now I want to kind of come back to the microscopy side of things where, from condensed matter, we look at these phase diagrams, and something like 20 Kelvin is actually, to some of the physicists who I work with, is actually pretty warm. So they don't even consider that very cold, right? But this becomes a big challenge for thinking of more advanced questions we can ask in the electron microscope. Although I want to also provide some historical context that this was not always the case. And so, there's been a big resurgence that I'll mention in a minute of trying to push towards lower and lower temperatures. But actually, this is something that was done many decades ago. And so, for instance, here on the left, what you see, people actually studied the superconducting state in electron microscopes from very early days of electron microscopes. And so here on the left, actually what you're seeing is a shadow image. So as you cool a material down through its superconducting transition. So this is just superconducting lead. And remember, I told you that superconductivity is not just zero resistance, but also the expulsion of a magnetic field. Now, we all know that electron microscopes steer our lenses or steer our electrons with electromagnetic fields. And so if you start messing around with the magnetic fields in the material, you're going to see that in the image. And so these sort of fuzzy boundary images that you see, that's what we call sort of the mixed state of superconductivity. That's where some regions are expelling magnetic fields and some regions aren't. And so what you get is this kind of wibbly sort of boundary. You can't clearly resolve the boundary of that material as it's sort of only partially superconducting. Now, there's been other examples, so slightly more recently, early 90s work of looking at also superconducting vortices. And so this is, again, another thing that happens in superconductors with the magnetic field. So all of these little bubbles that you see in the Lorentz TEM image are those superconducting vortices, and they can track them as they go up and down through these superconducting transitions. And so you notice from both of these plots, actually the temperatures are very low. So on the right, something like 6 or 7, on the left, something like 6 or 7 Kelvin, on the right, something like 4 to 5 Kelvin. And these are experiments that actually many groups around the world were doing. But the microscopes that they were using had some sort of different demands, right? And so if you think about the really high resolution tools that most of us use, or many of us use today, we have much narrower pole piece gaps, so we have a lot less room at the sample. And many of us use side entry microscopes because there are a lot of advantages in terms of flexibility, and especially at shared user facilities, there's a lot of compatibility benefits to having these side entry high resolution stages. So some of this work, some of the temperature capabilities were possible in the past. What we'd really like to do is to be able to reach these very low temperatures, but maintain the amazing spatial resolution and other kinds of control that we now have in the modern electron microscopes. And there's many people around the world who are starting to push on this. I particularly want to highlight really the leadership and the contributions of Lena Kirkudis, who was my PhD advisor, who we sadly lost a few years ago. And so I'm not going to say too much more about cryo, just to say that, I think she was really, especially from the context of women in microscopy, not just a woman in microscopy, but really just a figure in microscopy that I think many people looked up to. I know many people looked up to very well. And so just to highlight one of her many kind of contributions and advances to the field was really pushing and leading the development of these high resolution techniques, pushing to lower temperatures. And so it's great to see not only the progress that she has made, but really the way that that's been and being kind of carried on in the field as we go forward. So very excited about that. And I think this is going to be a big opportunity for us as microscopists to interface again and kind of come back to some of these condensed matter problems that I'm interested in. Okay, so just to kind of come ahead a little bit more, so I told you about these nickelate superconductors over here on the left, but I showed you on the early plot, there's actually a new family of nickelate superconductors which have emerged more recently. They're sort of related in their structures. You can see that one of them is kind of missing oxygens and one of them has this like layered stacking. And we're still trying to figure out exactly how these materials relate to each other. But we've also started looking at the ones, these what we call Ruddleston-Popper materials over here on the right. So these, unlike the other nickelates, were actually a kind of more of a surprise to the field. They weren't initially predicted. They kind of came out of nowhere. And now we're trying to figure out what's going on. And the first discovery of superconductivity was in bulk crystals, again, at very high pressures. So not as high, like 100 GPa, but still 20 GPa, which is, nothing to sneeze at. And from X-ray measurements, it was noticed early on that the onset of superconductivity seemed to correlate with an onset or a change in the crystalline symmetry. And so this again goes back to this idea of very close coupling between the lattice structure, the electronic structure, and the functional properties of these materials. So we can't really do electron microscopy under high pressure conditions at this point. But what we can do is we can work again on thin films with that strain that I told you about. And so some of our collaborators were able to show that instead of using high pressure, you can actually use the substrate to push on the lattice, and you can again stabilize superconductivity that you're seeing here down in this trace on the bottom. So that's where we kind of got very interested, and we thought, okay, this is something we can put in the electron microscope and we can understand what's going on at the atomic scale. So instead of just looking at one sample, we actually wanted to look at a whole series. And so we look at not just the compressive strain case that is superconducting, but all the way up again, going back to that other direction of tensile strain where we're now pulling on the material. And so again, a close collaboration with the synthesis folks who are able to grow a series of all of these different samples. And so this is a lot of work that has been part of the PhD work of Lopa Bhatt, who's here at Cornell, where you can see she's been able to go through and image sort of all of these different films under these different strain configurations. Now, this is where we need to really turn to the most cutting edge electron microscopy. And so what we're particularly interested in these nickelate, in these new nickelate superconductors are actually the positions of the oxygen columns. And I'll tell you why in a minute. But many of you will know that imaging light elements with high resolution and high precision is very tricky in these crystalline materials. And so we're really lucky that this scientific question coincides with the really sort of launch and development of this multi-slice electron ptychography technique that has been developed, which gives us access to very high resolution and high precision measurements, even of those oxygen columns. So here you see a comparison with some of the other imaging modes. And clearly, the MEP right here in the middle gives us all of those lanthanum nickel columns, but also all of the oxygens that we need. So I don't want to go too much into the details of ptychography. There's many people on the call who know more about it than I do. But the idea is that now by collecting sort of the full diffraction pattern after it passes through the crystal, instead of just using an annular detector, we can do an iterative reconstruction algorithm, right? And so the idea is that we can actually, if we collect the exit wave function, we can actually reconstruct what potential it encountered or what the sample was, the grading that it went through as we went through the material. Now, we can also do this not just we need to do this for thicker materials, actually through a multi-slice technique, which means that we have to kind of break the sample up into these different vertical slices. And so actually, although this is kind of computationally challenging, it has an experimental advantage that we've now started to regain some of that Z resolution that we tend to lose in a more conventional STEM imaging. And so we can see not just one projection of the sample, but we can actually start to differentiate some of those slices with a spatial resolution of a couple nanometers. And so this is a ptychographic reconstruction that Lopa has done as we cut through the depth of the sample. And so here you see these oxygen atoms. My cursor maybe came back, but you can see very clearly. And as it goes deeper through the sample, you can actually see how the oxygen columns actually even swap in the crystal, right? So this is an unprecedented level of access to these atomic structures that we haven't really had in the past. And so what LOPA has been able to do is to do these tychographic reconstructions across that whole strain series, where again, you can see sort of the beautiful resolution that we have, but this really opens up to a lot of quantitative analysis. So for instance, one thing you can look at is these nickel oxygen bond angles. And you can immediately see now a difference between the samples on the left, where all of the bonds are pointing in the same direction. In this case, they're all pointing out away from that central plane, and the ones on the right, which are under the tensile strain, where you have this alternating bond distortion. And this was something that hadn't been characterized before, has not been seen before. And so this is really the first sort of insights into this strain-dependent sort of symmetry that we see actually in these two different crystals. And what's amazing is that we take these bond distortions and some of the other measurements that she can do, we can turn these into basically atomic models for each of these thin films. And if we compare those atomic models from the strained thin films with the atomic models from the original discovery paper of superconductivity in these samples, what we find is that our atomic model for the superconducting thin film is very, very similar and has basically exactly the same symmetry as the atomic model for the superconducting nickelates under high pressure, and that our tensile strain samples are very similar to the kind of ambient conditions where there's no superconductivity. So already this is kind of a really compelling agreement, but the last sort of step that we're able to do is now, so Edgar is a postdoc in my group in Dresden, is able to take these models and actually perform more advanced theoretical calculations. So here we're looking at the band structure of these energies. Again, I don't want to go into the details, but these are all sort of topics of consideration that are in these very pressing in this nickelate field sort of today. So just to kind of overview this project, you know, what I love about microscopy and sort of the corner of it that I work in is actually we get to be a part of these big team collaborations. And so we work with experts really spanning synthesis theory, and we hope to provide the expert characterization that gives us really unique insights to these quantum materials and can help us really advance our understanding sort of as efficiently as possible, always with the goal of understanding so that we can design better materials in the future. Okay, and so just to flash a few last things, you know, we can do everything I told you about our, you know, nickelate superconductors, but obviously these, you know, this logic extends far past that. So some of the other things that we're really interested in are, for instance, understanding and being able to kind of help almost refine new metastable structural phases. So sometimes you can grow materials as thin films that you actually can't stabilize in bulk, which means even just understanding where the atoms are can be very complicated. And so STEM obviously has a lot to contribute over there. And also, you know, not just superconductors, not just oxides, not just thin films, but there's all kinds of other materials. And so, for instance, in these bulk crystals you see here on the right, we're actually looking at sort of subtle differences in the symmetry of the atomic lattice. And these are sort of what we call quantum magnets with very interesting spin textures that can be useful for different sort of functionalities as well. So it's a huge range of materials, but we always come back to sort of the same kinds of tools and the same kinds of questions. And I mentioned before that we're also interested in expanding to, you know, lower temperatures. That's just one aspect of the phase space that we want to move into. So we already have access to electromagnetic fields through, you know, sort of modifying the lens conditions in the microscopes or using biasing holders. I talked a little bit about temperature and how we can push that even lower for some of these condensed matter systems. And thinking about how we can also start to couple in some of the other relevant phases or stimuli on these materials. So for instance, also mechanical stress or thinking about, you know, pressure, which obviously relates to these superconductors that I just told you about. And the last thing I'll say is that everything I talked about is, you know, these sort of quantum materials, and it skewed more in this kind of condensed matter sort of framework. But there's this really exciting development that I see coming of quantum materials to other applications. And so this is actually a quantum material which has been now seems to be very promising actually as a catalysis through a group in Dresden that I'm working with. So moving towards sort of new energy applications, but based on these same kinds of materials and other kinds of quantum materials which can be used for sensors or actuators. So this material on the right has a really impressive giant magnetorestriction, which can be useful for, micro robots or resonators or what have you. Okay, so I think I'm coming up in the end. And so I'll just quickly, you know, try to thank some of the people who have contributed to this work. It was actually, normally I'd like to show the pictures, but everybody doesn't quite fit because it's, you know, I feel very lucky to get to be part of these big, very team-driven collaborations. And so you see The picture on the top left is actually us at the Superconductivity Gordon Conference in Switzerland last spring. This is kind of Team Nicolates. So from all groups around the world, we're all interested in Nicolates. And then my group in Dresden over on the right at sort of our peak height this summer, but also many of the collaborators you see on the slide and many more who on projects that I didn't have time to talk about. So with that, I hope that there's still some time for questions.
Yeah, thank you so much for this amazing talk. I really enjoyed it. Yeah, and superconductivity is super interesting and just like there's a lot to explore essentially. So we have couple questions coming in. One is by Chris Sharp. He says, "Thank you for the awesome talk, Barrett. And since the Nicolate samples require careful reduction to remove oxygen, how stable are they in ambient conditions, particularly in regards to oxygen exposure?"
Yeah. So what's really interesting is that we found early on they were not very sensitive, and so we did a lot of checks right at the beginning, because we all sort of thought, us and the synthesis folks thought, oh, they'll really want to take back oxygen, and they didn't. And actually, as the sample quality has improved, it seems like they're getting more and more sensitive. So again, we don't really have exactly a microscopic understanding of how the oxygen is actually moving in and out of these crystals. And so now we do take a lot more precautions to make sure that they stay in the sort of the reduced phase. They're not so crazy air sensitive like some other materials. We basically we store them under vacuum when we're not working with them. The advantage of electron microscopy is we actually have, now that we understand how the oxygen excess or deficient oxygen sort of manifests in the crystals. One of the things, for instance, is as they uptake oxygen, the C-axis expands. And so that's great for us. When we do lattice imaging, we can just kind of check, okay, is the C-axis still where we think it should be, or has this material oxidized and we need to get a new one? But yeah, they will start to suck back in oxygen over, months kind of time scale if you leave it sitting out on the.
Interesting, cool. Yeah. And then Santanu, he has a question. I have a question. Yeah, okay. Sorry, it's like scrolling up. And not about superconductivity, but about MEP. MEP reconstructions are often done with very high doses and reported several hundreds of microsecond dwell time. Is there any way to accelerate MEP acquisitions at lower doses, shorter dwell times?
That's a great question. So I will say all the parameters of the tychography for that particular work are reported in the methods of the archive. So definitely check that out because I don't know it off the top of my head. So at Cornell, we mostly use what is now the second generation of the Thermo Fisher MPAD. And so that is also a faster readout. And again, I know depending on which detectors you have, you can go faster or slower. I think so. In some cases, actually, tychography can be much more dose efficient than actually HADF-STEM imaging, for instance, because you're taking advantage of more of the electrons that pass through the sample. Whereas in ADF-STEM, we're really kind of wasting a lot of electrons because we only collect those few that make it out to high energies. So in some cases, it is more dose efficient. But going to shorter dwell times is really important for when we want to do low temperature measurements. And so I know that, so we have done some work, extending tychography to cryo. And so in particular, I know Lopa Bat and Noah Schnitzer, who's now left Cornell and gone to Imperial, have both reported in various M&M abstracts, some really amazing cryotychography, again, but it requires having a very fast detector. And I would say the best advice I can give to people who want to do low temperature measurements is take, 5 to 10 times as many data sets as you think you need, because the yield is a bit lower in terms of which ones actually turn out nice.
Yeah, that's super exciting, like tychography and cryo. I mean, I think it's a floor, field that needs to be.
It's going to be great. Yeah. So we're getting there. It's definitely getting there. Yeah.
Yeah. So Daniel Ugarte asks, could you comment on the reliability of the confocal multi-slice tychography, which is kind of on topic? In fact, for a STEM longitudinal resolution is usually about 7 to 9 nanometers. And are you getting about 2 to 3 nanometer longitudinal resolution in confocal microscopy?
Yeah, and again, I'll refer you to the more technical tychography papers for the details on that. But my understanding is this is sort of a limitation really of the computation and the algorithms that are working these days and how fast you want the information out. And so 2 to 3 nanometers is kind of the Z resolution that we're working with now. I think there's definitely going to be there are efforts I know to push that even lower, towards 1 nanometer or even less. And so people are definitely moving in that direction. As far as I'm aware, it's not quite there yet. But it's pretty, I think in many cases, it can be very reliable, and it does really help, for instance, in some cases, to have the additional information of that kind of Z depth. So for instance, in the nickelates, I showed you this example where the oxygen kind of distorts as you go through the plane. And the problem is in a full projection technique, then the whole column just looks like an ellipse. And so you can't do that kind of quantitative analysis. So I guess to sort of answer your question, 2 to 3 nanometers we're really happy with because it's better than nothing. But
Right.
It will also as that resolution even improves in Z as well.
Yeah, for sure. So Kate Reedy asks, says, thanks, Barrett, so cool. I was curious in with adding pressure to the superconductors via strain, do you find epitaxial strain may have slightly different effects to hydrostatic pressure, even just for Poisson ratio? And secondarily, do you think we could ever apply hydrostatic pressure in the microscope?
Yeah, so the first question is absolutely. And yeah, maybe I'll put you in touch with our reviewers. Yeah, epitaxial strain and hydrostatic pressure are not the same, primarily because as Kate has pointed out, you have the Poisson's ratio. So in hydrostatic pressure, we're pushing on all 3 lattice directions. And the assumption is usually that it's pretty isotropic. In epitaxial strain, we only push on 2 lattice directions and the third is left to relax. And so in most materials, if you compress, the third direction is going to expand, or vice versa. If you expand 2 directions, the third is going to compress. And so that is something that we were really interested in with these nickelate superconductors, because there was a lot of discussion about the sort of out of plane axis as an important tuning knob for superconductivity. But in fact, when we compare the epitaxial strain to the high pressure samples, because of this Poisson's ratio question, what you find is actually something completely different. And so the hydrostatic, the bulk samples, superconduct when the C-axis is small, but the thin film superconduct when the C-axis is large. And so that's, I think one of the key questions in this field, and that's one of the things we were hoping to address. And so to get to your question, we can look at epitaxial strain in the microscope. We love that because it's static strain. Doing hydrostatic pressure, I think, is less obvious to me. And so, we're very interested in kind of working right now on uniaxial pressure. But hydrostatic pressure, of course, the challenge is the third dimension, right? Yeah. So there, maybe, I don't want to say never, because there's people smarter than me out there who will figure out how to do it. But, maybe with some kind of very specialized, you need almost like a liquid cell, because you need a pressure transmission medium, but I don't know how you would get it to transmit pressure sort of along the optical axis. So maybe, but it's not obvious to me. So we're very happy with the thin films that we have access to.
Yeah, it would have to be a very specialized cell. Like some engineers will figure it out, I'm sure.
Yeah. I see Vinayak in the chat, so I'm gonna leave that to him. This seems like right down his alley.
Maybe he can comment. Yeah, so there's another question by Lucio Dentis. Thank you so much for the talk. Do you see recent advances in TM and tychography extending beyond functional materials to advance our understanding of novel structural materials like high entropy alloys?
Yeah, absolutely. And what I think is so cool is like how all of these fields really are kind of, continue to sort of converge in exciting new ways. And so I mentioned, we're doing uniaxial pressure. We've been doing it on quantum materials because, again, in the kind of condensed matter community, this is a known tuning knob. But actually, the groups that we're working with who have been developing these are actually approaching it from the perspective a lot of times of these kind of structural materials or alloys or whatever. And so, we're doing experiments, and our colleague and our collaborator has been doing these on, I think like sort of steel compounds, or I'm going to apologize if I get it wrong. I think Lynn was on, so she will correct me. But, if you can do it also on structural alloys, and you can even start to mix in things like oxidation and whatever to see how those materials can decay under stress. So it's all pulling, I think, from the same toolbox and trying to get at new questions. And that's also what I love, is like being able to pull inspiration from kind of unrelated fields and pull them into, the questions that we're interested in.
For sure. Yeah, there's one last question before I guess we're running a little bit far on time, but I think Chess Adam Chowdhury had a question that says, so epitaxial strain compensates the high pressure requirement for superconductivity behavior in nickelates. I think that's posed as a question.
Yes, and that's basically what we're seeing, and I would say, exactly why that is what we're trying to understand. And so what's really amazing is that If you push on these materials from all three directions, you can get superconductivity, but it seems that if you push on them from two directions, you can also get superconductivity. And so trying to kind of remedy those and relate those two statements to each other is exactly what we're interested in. And really, this is like very fresh and ongoing work. It's a very active field. And I think, we don't yet know the answer, but that's certainly what we're hoping to understand.
Awesome. Yeah. So I think we'll take a break right now. Thank you so much. And then in a couple minutes, we will start the panel discussion.
Great. And thank you, everybody, for the awesome questions.
Thank you so much, Barrett. And also, if you do have questions in the Q&A still, and Barrett, you have time where you want to, you can answer them in the Q&A. So if your question didn't get answered, don't worry. Thank you so much for such an amazing talk.
Yeah, great. I will see what I can get to. I might have to run, but also if people want to reach out, I'm very easy to find on the internet. It's just me with my name. So feel free to Google me and you'll find an email and just reach out.
Perfect. Thank you.
Thank you.